Okay, now's the time to modify our equation for energy when we have friction, when we have other forces, pushes and pulls acting on our object, where the kinetic and potential energy doesn't stay constant throughout the whole problem. Our current equation that we've been using is that delta U, the change in potential energy, plus the change in kinetic energy is equal to 0. The problems we've looked at have involved only gravity and springs. Gravity and springs only transfer energy between potential and kinetic only. That's it. But friction, for example. If you have friction acting on an object, friction will take some of the potential and kinetic energy away and turn it into heat, thermal energy, for example. So we need to modify this equation slightly. So it will take into account the energy that our forces change or transfer in our system. The transfer of energy from one form to another is called work. So work is an actual transfer of energy into or out of an object or a system. So, for example, I can give my calculator energy by pushing on it. By pushing on it, I am making it move, thus giving it kinetic energy. That would be an example of doing positive work, because I put energy into my system. If I slide the calculator and let friction bring it to rest, that would be friction is taking energy away. The calculator had kinetic energy that I gave it, but now the kinetic energy is gone. It hasn't turned into potential energy because it hasn't moved vertically. It's not connected to a spring. So that kinetic energy disappeared. Now, it's not that it's gone altogether, it's just in a different form. It's not in the form of potential or kinetic energy of the calculator anymore. There would be a little bit warmer surface between the calculator and the table now because of the friction. So friction would be doing work. Work is the transfer of energy from into or out of an object or a system. Work is actually really easy to find. If you remember back to how we derived the equations for potential and kinetic energy, we had our force, whether it was the force of gravity or the force of the spring, and we set it equal to ma, but then we rewrote a as dv dt, and then we rewrote it as v dv dx. Brought it to the other side and integrated. That is the work. Work is the integral of whatever force. It doesn't matter what type of force. Whatever force is being applied times dx, the distance that the object has moved as that force was applied. So number one, to do work, to put energy into a system or take it out, your object has to move. I could sit here and push on this wall all day long and get really, really tired, but I would not do any work on the wall because I haven't moved the wall. The only way to do work on an object is to physically make it move. Okay? Now, I would get tired because my muscles would be contracting, so my muscles would be doing the moving, but there would be actually no work done on the wall. So work is the integral of force with respect to position. So that means we need to know what the force is. If the force is changing, we need to know the equation that describes the force so that we can integrate it. If the force is constant, that's fine. We put the constant value in and the constant comes out. So if the force is constant, the force will come out of the integral sign. Integral of dx will be just some distance, the final position minus the initial position. Now there's another piece of information that's very important here.